Alrighty, welcome back from break, nerds. Like I said before I started the video, we're going to be starting chapter 6 today. And chapter 6 begins with arithmetic of functions. Adding functions, subtracting functions, multiplying functions, and of course dividing functions. In order for you to be successful with this, you must understand function notation. This says f plus g of x. It does not say f plus g times x. When this goes wrong, that's how it goes wrong. Students think this means they're supposed to multiply by x. No. F plus g of x means f of x plus g of x. This is just a smaller way of writing it. Less characters. It's function notation. And the reason why we can write it like this is because when you add two functions, the result is also a function. So one more time, and maybe write it down. This doesn't say times x, this says of x. This means you will have a new function, and x is its variable. This new function is found by adding f of x and g of x together. If you can simplify it by combining like terms, you do. Cool? Okay. Again, it's just understanding what this is saying. F minus g of x, not times x, of x. That means function f of x minus function g of x results in a new function. X is its variable. But here's the thing. Order of subtraction matters. Order of addition does not. F minus g of x is not the same as g minus f of x. It is the student's job to pay attention to the order of the letters. Order matters when subtracting. Please watch out for it. In mathematics, when you put two letters side by side, that means multiply those two things. But f and g are the names of functions. So when you see fg of x, what it's telling you to do, and this is not fg times x, this is of x. When you see fg of x, it's telling you, take function f of x and multiply it with function g of x. Multiply the two functions and see what you get. If you can simplify, do that. If you can't, okay. So when could you simplify? Like the questions in the homework. Distribute, things like that. Okay. Like addition, order of multiplication doesn't matter. So fg of x is the same as gf of x. It doesn't really matter. Order of multiplication doesn't matter. Just again, when this goes wrong, it's because students think this says, oh, and multiply by x. That is not what that says. F and g are names. X is its variable, okay? Typically, when you get your new function, you would use a third letter to name it. And my personal favorite, because it allows me to talk about things that we did earlier in the year, is quotient of functions. F over g of x. Once again, this does not say times x. I've said that all 4 times now. And students are still going to get that wrong on the test. Don't multiply by x. F over g of x is f of x divided by g of x. And because g of x is a function, it has the possibility that it might be able to be equal to 0. But you can't divide by 0. So when you do f over g of x, you just have to make sure that g of x cannot equal 0. Domain restrictions. That should sound familiar. We've talked about restrictions of domains of functions several times this year. Just like subtraction, order of division matters. F over g is not the same as g over f. It is the student's job to understand what the function notation is telling them to do. Remember, you can never divide by 0. So the bottom of our fraction can't be 0. says at the bottom of the box, in each case, the domain of the new function consists of all numbers that belong to both the domain of f and the domain of g. And in words, that's a little abstract. So let's get through the 5 examples down here, and I'll get to highlight more what this is talking about. See all this space I left us? Don't write too large. It's still going to be tight. Let me show you your homework. See how that looks like 2 questions? But if you read the directions, it's actually 1, 2, 3, 4, 5 for each one of these. And that is why I gave you the whole front, because that's actually 10 questions there. Then there's more on the back. Okay? So I left you all this space because this is 10 questions. Okay? Okay. Just making sure I'm saying that. They're not difficult. It's just that you need the space. This is 5 questions. We have an f of x, we have a g of x, and what we're going to do is we're going to build 5 new functions. You know, the neat thing about functions is when you perform arithmetic with functions, adding, subtracting, multiplying, or dividing, the result is always a function. It's really, really neat because there are certain kinds of mathematics where that doesn't work. It always works in algebraic systems, which is why this course is called Algebra 2. So you don't know this, but in mathematics, algebra is actually an adjective. It describes a world where certain things work. And specifically, adding, subtracting, multiplying, dividing work in those worlds. And then we call them algebras. Okay, just so you know. Alrighty. Our job is to build 5 new functions and give the domain of each one. Cool beans? Let's go. And I'll use 5 different colors because there's 5 different questions. We'll start with orange. Let's do f plus g of x. This tells us take our f of x and add our g of x. That's all it says. Our f of x was x squared. Our g of x was the square root of x plus 1. These are not like terms. I cannot clean this up at all. That's it. Finito. Okay? There. You just created a new function. X squared plus the square root of x plus 1. But we have to talk about what its domain is. Well, you could square any number you want. So this part of our function has absolutely no restrictions. But square root bars. What kind of numbers can I not take the square root of in the real number system? Negative numbers. So we have to make sure that x plus 1 is not negative. You might recall me saying things like, oh, okay, not negative means x plus 1 is greater than or equal to 0. Subtracting 1 from both sides tells us that x must be greater than or equal to negative 1. So our domain is negative 1 to infinity, including negative 1. You guys remember way back in chapter 1 and then also in chapter 2 when we were finding the domains of functions algebraically? Here it is again. It's almost like I've been preparing you for this since the beginning of the year. But it's not that bad, is it? Any questions about adding these 2 functions? How about questions about finding its domain? None yet? Okay. Then let's continue. I'll write in blue next because go Gators. F minus g of x. Order matters. Make sure you know that this says f of x minus g of x. That means x squared minus the square root of x plus 1. Yeah, that's it. I mean, there's nothing else you can do. They're not like terms. You can't clean them up in any way. Boom, there it is. And it doesn't matter if that square root bar has a plus sign or a minus sign in front of it. You still can't take the square root of negative numbers. That means this blue function, f minus g of x, has the exact same domain as my orange function, f plus g of x, which was -1 to infinity, including the number -1. Yes, sir. Will it always happen is a great question, and we will answer that question in a moment. But really good question. Let's find out what happens. Maybe multiplying changes something. Let's see. fg of x. That means your function f of x times your function g of x. So our f of x is x squared times means just stick it next to g of x, x plus 1, and look, you still can't take the square root of negative numbers in the real number system. So this thing's domain is still the same. Before we move on, I want to point something out. Look at the original two functions, f of x and g of x. F of x is a quadratic. You could square anything you'd like to. This thing's domain is all real numbers. This has absolutely no restrictions. F doesn't give an F. What letter or what number you try to plug in. Because it's just squaring it, no big deal. But g of x cares. You cannot take the square root of a negative number. G of x's domain is -1 to infinity, including -1. And notice adding, subtracting, and multiplying gave us g's domain. But why only g's domain? Because g was the restrictive function. Function f said, use whatever numbers you want. And function g said, well, no, you can't use anything you want. I'm only going to let you use the numbers -1 to infinity. It's kind of like when you ask your parents, separate from one another, something you really want to do this weekend, right? Like, for example, when I was 17, I wanted a tattoo and I wanted an eyebrow piercing. My mother said, my parents are divorced. My mother said, obviously your father has to be okay with it, but I'm okay with you having the piercing, but not the tattoo. So then I asked my dad separately. And my dad was, well, obviously your mother has to agree. I'm okay with the tattoo, but not the piercing. So guess what I got? Nothing. And that's because both parents said no to different things. So overall, I got nothing. If one parent had said, get them both, and the other had said, you can only have one of them, well, then I was only going to be able to get one of them because I don't want either one of my parents to be mad at me. You see what I'm getting at here? The more restrictive thing is going to be the boss of the domain if one of them doesn't care. Cool with that? Okay. Now let's go do some division. F over g of x. Oh, by the way, I got my tats and piercings when I was 18 because then they couldn't tell me what I wanted anymore. Then it was my body. All 9 tattoos and my eyebrow piercing. Yes, I have 9 tattoos. I miss my eyebrow piercing. I miss it so badly. Oh well, you gotta grow up eventually, right? Don't grow up, it's a trap. Now, a moment ago, Jarrett asked me if the domain was always going to be the same. Well, the answer is it depends on what kind of math you're doing with the functions. Because g of x still has the same restrictions. G of x is never going to allow me to use a number to the left of x equals -1. But I've introduced a new restriction because this is a fraction. And what's the only rule about fractions, Daniel? The denominator can't be 0. You see, g of x doesn't care if x plus 1 is 0. The structure of the function cares, though. So because this thing is in the bottom of a fraction, I can no longer have that x plus 1 is equal to 0. Now I have to say x plus 1 is strictly greater than 0. So subtracting 1 from both sides gets me that x is greater than -1. So no, the domain can change. That domain actually got smaller, didn't it? The last example is kind of fun for me. One, because its name is fun, GG. If you're a gamer, you know. Two, the math does something neat. Let's find GG of x. Yeah, GG, that's what I was thinking when I was grading those tests. All right, so we got g of x times g of x. Oops. Now, wait a minute. When you multiply something to itself, what is that telling you to do? What is it? Square it. So this is actually saying whatever your g of x is, square it. Fine. Let me take my g of x and let me go ahead and square it. Oh, look. Squares and square roots cancel each other. GG of x, it would be written like that. GG of x is just x plus 1. What kind of function is x plus 1 if you had to describe it? Linear. It's a straight line. But what is the domain of linear functions? Everything, right? All real numbers. Now let's go back and let's talk about my piercings and tattoos example that I gave you a minute ago. One parent said, no tats. The other parent said, no piercings. So when I was 17, guess what I got? Neither. Not both. I didn't say, I'll just make you both mad and I'll get both things. No. Restrictions are restrictions. This thing's domain is not all real numbers. And that's because this is just a cleaned up version of this. And this has a square root bar in it. So this has a domain restriction that x must be greater than or equal to -1. So the domain of our function is -1 to infinity. It's literally a straight line that begins at x equals -1 and goes to the right. I'm going to pause the video because I'm going to switch over to Desmos so you all can see a picture of this. Unfortunately, this is recording my document camera, so it won't be able to see Desmos. So let me pause the video. Anyway, back to the video. So once again, you always determine your domains before you simplify. Okay? Determine your domains before you simplify. Now, as it turns out, adding, subtracting, multiplying, dividing functions, these are not the only ways to build new functions. There's another way, which I think is a lot of fun, because I'm a big old nerd, called compositions of functions. I mean, in music, composition literally means to create. When you compose two functions, you create a new function. But composition in mathematics means plug one function into the other function. I need you to see that that is not a dot. That is an O. It's not a dot. It's an O. Let me show you a dot. That's a dot. That's an O. And they mean different things in mathematics. The little O stands for of. This is read as f of g of x. Sometimes we'll be lazy and say fog x. We'll be lazy and say that. But it's read f of g of x. It's the same thing as writing it like this. Maybe it would help you to see it in colors. It means everywhere that f had an x, you're going to put a set of parentheses and replace it with something else. That should sound familiar to you. Like all horizontal transformations. Everywhere you had an x, you put a set of parentheses and you replaced it with something else. You didn't know this, but all horizontal transformations are compositions of functions. You just didn't know it yet, that it had a special name. So yeah, it means go to your f of x. Everywhere there was an x, you put a set of parentheses. And then in those parentheses, you will drop in a new function. Okay? And just like before, the domains are always going to be determined by the original functions. But now that we've talked about arithmetic of functions and compositions, I can make one generalized rule about domains. When creating a new function from other functions, your domain can never get larger than what the originals allowed. They can stay the same as the originals, or they can become even more restrictive. Remember, one parent said I could have tats. The other parent said I could have piercings, which meant together I was allowed to have nothing. Because that was the most restrictive, which was the safest way. I didn't make any parents angry until I was 18. Okay? When composing, no new numbers can be added to the domain. Okay? And just like subtraction and division, order of composition matters. It's the student's job to pay attention to the order. And if it helps to see it in color, this one says everywhere g had an x, you'd open a set of parentheses and drop in the function f of x in its place. Students need to be able to see the difference between fog x and gof x, f of g of x and g of f of x. Gof, G-O-F. I'm going to be real with you. I never write fog x or gof x in my own work. So if a question has this little O in it, I always default back to this format because this format shows me exactly what was being plugged in and where. So I prefer this format. We okay? Let's actually put it to use. And you know what? I'm going to do these notes out of order. I want to come all the way down here and show you how to compose functions, okay? And then we'll go up and do the last question. I just want you to see how it works. And I'll do f of x will be my blue one, and g of x will be my red one, just so I can show it to you in colors. Yes? All right. g of f of x, a. G of f of x. So everywhere g had an x, I open a set of parentheses and I drop in whatever f of x is. F of x happens to be x squared minus 1. Red and blue makes purple. These parentheses are not serving a purpose. No, you cannot take the square root of that x and the square root of that 1. You can't do that because this is subtraction. You can only do that if it's multiplication. The directions were to find the domain of this thing. We've done these before. In fact, we did them at the end of last chapter. Now, did we do them with square roots? No, but we did do them with what's required, and that is the sign diagram. Because remember, you can't take the square root of a negative number, right? That means whatever's underneath that radical better be positive or 0. So you factor it. We did do these in chapter 3. Quadratic inequalities. And the only way to solve them is by using a sign diagram. This has two critical values, x equals -1 and x equals +1. So you draw yourself a number line, you throw your critical values on it, and you test to the 3 zones, looking for positive and negative. If you grab a number to the left of -1, like -2, and drop it in here, -2 plus 1 is negative, and -2 minus 1 is negative, that product will result in a positive number. Grab a number between -1 and +1, like 0. I love 0. 0 plus 1, ooh, wrong pen. 0 plus 1 is positive. 0 minus 1 is negative. And the product of those kinds of two numbers will be negative. And grab a number to the right of 1, like 2. 2 plus 1 is positive. 2 minus 1 is positive. And that product will once again be positive. It says greater than or equal to 0. Was I looking for positives or negatives? Say it louder, please. Positives, yeah. And since it has the equal to bar on my two critical values, open dots or closed dots? Closed dots, big old closed dots. And Daniel said we're looking for positives. Positives were to the right of 1. And positives were to the left of -1. So our domain is those two zones. To the left of -1, so -infinity to -1, inclusive. To the right of 1, union, inclusive, 1 to positive infinity. And then lastly for part A, it says evaluate for x equals 4. That means plug in 4 and see what you get. Let's plug in 4 and see what we get. G of f of 4. G of f of 4. That is the square root of f of 4. But what is f of 4? Well, that's just 4 squared minus 1. 15. Let's see. Where do I have space? There, just showing you what we did. All right. Questions, comments, concerns about building the composition of functions? How about finding their domains? How about evaluating? There was a lot of skills in that one question. No? Everything felt comfortable? Just a new way of seeing old material put together? It's really what that is. Okay, then switch the order. Let's do f of g of x. See, I don't like to use the little o. I prefer it like this because it shows me exactly what's going where. Everywhere f had an x, an x, I said that right. I'm going to put a set of parentheses. because it used to say x squared minus 1. Now in those parentheses, I have to drop in function g. Determine your domain before you simplify. Because this x is underneath a square root bar, what do we know about this x? Can't be negative. So what we know is x is greater than or equal to 0. So even though this thing will clean up to a linear function, oh, it's supposed to be purple. Red and blue makes purple. Even though it cleans up to a linear function, its domain is 0 to infinity. Good? Okay. And let's evaluate f of g of 4. You know, you could figure out what g of 4 is and then plug that number into f, like I did with this one. Or you could just put 4 into right there, because this is f of g of x. So you could either figure out what the values are before composing or what the values are after composing. It doesn't matter. Isn't that neat? I think it's pretty neat. I think it's pretty neat. Cool beans? Yes, Mr. Ramp. Okay, great. Let's tackle this last one. Now, this last one, don't write large. We are going to be composing, but we don't have the functions. We only have x's with their y's. I know your paper is very dark. That says f of x. This says g of x. Okay? We're going to find f of g of x. We're going to find g of f of x. We're going to find those two as basically tables. And then we'll also write the coordinates as sets. Then we're also going to find the domain and range of both things. Before we start doing any of that, let's find the domain and range of these two. Again, red and blue, because I can mix those two colors and make purple, okay? Let's find the domain of f as a set. You ready for this? This symbol is called a brace. If you don't know how to draw those, that was a tall, skinny S and then a backwards, tall, skinny S. One more time. Tall, skinny S, backwards, tall, skinny S. Tall and skinny. Yep. So the domain of f is just the x values that you see here, written in order from small to big. F can only use the values of x 0, 1, 9, and 10. Those are the only x values that exist for f. And the range of f is the y values that exist for f, written in order, 7, 11, 12, 13. Get skinny. Crap, my paper crinkled. There we go. Let's find the domain of G. Once again, domain is the x values that exist, written in order from small to big, 4, 5, 12, 13. And the range of G are the y values that exist on G, written in order from small to big, 0, 1, 9, 10. All right. Now we're ready to actually compose these things. Now, when we were composing functions, which I actually think is easier than this, we were dropping a whole function into another one and then just listening to the symbols. Now we can't do that. Now, in order for me to find f of g of x, I had to evaluate f at everything that g of x could be. What does that mean? That means I have to know what f is when we have g of 4. But if you look at your table, what is g of 4? What is the value of g when x is 4? Say it. 1, yeah. So this actually says, what is f at 1? Because at x equals 4, g has a value of 1. So f of g of 4 says f at 1, because this equals 1. So what is f of 1? You come to your f table and you go, well, f of 1 is 12. The next value that x can take on for g is 5. So we go, all right, well, when x is 5, g has a value of, say it loud, guys. A couple of you whispered 0. All right, let's say it loud here. So what is f at 0 then? It's 13. The next value of x that g can take on is 13. So we say f of g of 13. So we go to x equals 13 on g, and we see that g's value at that x is 9. So this says to us, fine, what is f at 9? 7. And then the last value of x that g is allowed to take on is 12. So we say f of g of 12. See, this is more work because you have to actually evaluate it every single time. This is us building a table without the lines, just so you know. So you go to x equals 12 for function g, and you see that function g takes on a value of 10. And then you ask yourself, well, then what is f's value at 10? 11. That's as a table. This is as a set of coordinates. 1, 12. So 1, 12. 0, 13. These are the x, y's that this new function can take on. 9, 7. And 10, 11. So when you list out its domain and range, you just list its x's and its y's. Domain in order is 0, 1, 9, 10. Oh. Zero, 1, 9, 10. Well, that was the domain of f. That shouldn't be shocking, because f was the overall function. The range here is the y values in order 7, 11, 12, 13. Oh, that's the range of f. Once again, should not be shocking, because we were dealing with f. we were having inputs for f. F could only take on the x values in its domain, and f could only result in the y values in its range. And then, lastly, and more interestingly, let's change the order. Let's do g of f of x. Same trick, only backwards. Let's go g of f of the first value you can take on is x equals 1. And so we go to our f table, and we see at 1, f is a value of 12. We then go to our g table and go at 12, g takes on the value of 10. Cool. In our tables, the next x value that f was allowed to take on was 10. So let's see, f of 10. Oh, not my pen. Let's see, f of 10 is 11. Oh, so then we go to our g table and we say, what is g of 11? It's not here. Oh, you know what happened? 11 is not on the domain of g. So then what is g of 11? It's undefined because 11 is not in its domain. And that's okay. That's going to happen in the homework too. We can go to f of 0 now. And we can see when x is 0, f takes on the value of 13. 13 is on g's domain, and g of 13 is 9. Oh, I should have been switching to purple when I was writing on this right side. I'm sorry, I forgot to. The last value that x can take on for f is 9. So we see, all right, well, when x is 9, f takes on the value of 7. We go to g, and we say g of 7, 7 is not on the domain of g. So it's actually only 2 coordinates. G of f of x is only 2 coordinates. It's 12, 10, and it's 13, 9. It is a very small domain and range. Domain is 12 and 13 only, and the range is 9 and 10 only. It got very restrictive, didn't it? Whew. It's a big question, I know. I gave you one in your homework. But I'm hoping that it's not hard to understand. Do you have any questions for me about it? Yes, sir. Any way you could find the what? You mean the functions? No, these were just made up. You would need a lot more data, and that's only if a function can actually exist. Any others? Okay, since everybody's packing up, I guess not. All right, well. Thanks, nerds.